That's from Tatiana. Hi, Tatiana. Done. Excellent. Okay, guys, I think we'll make a start now. So, welcome to today's lecture. I hope the technology behaves itself. I want to recap on the work we've done so far on distance classifiers, and hopefully we can finish that off today and then move on to the main act of this course, which is neural networks. So that's the aim for today's lecture. Just to recap, we've looked at a distance classifier. A distance classifier uses physical distance in vector space to measure similarity between inputs, and therefore the closer you are to known patterns, you can give that classification to an unknown pattern. Now the equation for the distance classifier, just to remind you, if I can write it down here, is the summation I equals 1 to d of ai minus bi all squared. And it is square rooted, but we don't have to bother with the square root because both are monotonic functions, bi. And that is the distance between vector A and B. Share the screen, gosh, help. I'll be back in a second.
You need to go to Teams. Here. You share screen. That one.
That one.
That one. Microsoft Whiteboard.
It's slow here, isn't it?
It's not normally this slow. There's something being shown up there.
Ah, it's back here now.
Yeah, are we okay?
Okay, guys, can you see it? Yes, thank you very much. Right.
Is that the one you want?
Okay, are we online now? Great.
Yeah, they've seen this right screen.
Yeah.
Yep. So that's one. That's what.
Yeah. Okay. So, oops. Where's my? Right. That's where I was. Okay. Right.
Can they see that? Is that what they're seeing? Because they're not seeing the right thing. That's what they're seeing.
Are you seeing the whole picture or just the cross in the middle with an A on the right-hand side? Just a cross in the middle.
I can see A to the 2 to the 2 and a little graph in.
What's this one?
That's Tatiana's. That's mine.
You need to get you to full screen somehow. I don't know how we've got this screen back, haven't we?
You go now.
Yeah, no, that's the
Sir, you're sharing the app, not the screen itself. So because you're sharing the app, we are able to move it around ourselves on each individually rather than see where you're moving it. So you have to share the screen, not the app.
We're trying.
We're trying.
So I've not used Surface before, John. So I thought we're sharing the screen. Desktop. No. That's the Microsoft Whiteboard. That's the app. Oh, that seems to be working. Is that?
Ah. Is
That's
that better?
working. Yeah.
That's more like it, is it?
Yeah, you've got to look over here, John. What do you want?
Let's go back over.
You can't touch the screen at the same time I touch the screen.
Yeah. That's what.
Yeah.
Right, now they're seeing that. Is that clear, folks?
Yep.
Right, perfect. Right, after that false start, let's get cracking again. Right, we were looking at a distance classifier. We identified the Euclidean distance, and that is the summation over all dimensions of the vectors A and B of the square of the difference between AI and BI. And for true Euclidean distance, the whole thing is square rooted, but as I said before, that doesn't matter. Now, if the distance classifier is used for large problems, i.e. a number of classes, we only got A and B, but if we had, say, 50 classes or 500 classes. And if the vectors were derived from images, we might have 250,000 dimensions, and calculating this Euclidean distance becomes quite a computer-intensive task. It's not the summation that takes the time, it is the multiplication. So, to overcome and speed up the process, we identified, or two approximate distances have been identified which are faster. The first one is the city block distance, which is sometimes, certainly in America, it's called the Manhattan distance. And the second approximate distance is the square distance. Now, the definition of the city block is the summation over all dimensions of the modulus of AI minus BI. Now, to calculate the modulus, it is computer intensive, pretty low. It's one subtraction, which is the same as one addition, and then we ignore the sign bit. So it is much faster than the squaring operation. Now, what effect does this have in the pattern space? You should know that the contour of equidistance, which is the points which are all at a fixed distance from a point A, if I'm using Euclidean distance, it should be a circle. Now, what happens if I'm going to use the city block distance? And I think last week I left you with a problem to find the contour of equidistance 1 from pattern, which was point A equals 2, 2. So there is the point A on the graph. And we want patterns that are 1 using the city block formula from AA. Could anybody suggest one pattern point which might be unit distance from 2, 2? Silence. 2, 1, excellent. 2, 1, first dimension is 2, second dimension is 1. It is that point there. Another one, please. 1, 2, 1, 2. Another one, please. 3, 1, 3, 1. And another one. 2, 3. Now, at that point, you might assume that the contour, the line joining those 4 points, it could be a circle. But if you made that assumption, you would be wrong. Can I have a fifth pattern that is a distance 1 from 2, 2? Silence. Fifth pattern. If we were in the class here, I'd start dishing out 50. Eggs, thank you. You've won 50 pence in virtual currency. 2.5, 2.5. It will be 2.5 there and 2.5 there. It will be that point there. Ah, it's not a circle. And in fact, another point would be, oh, get away. Where's that come from? Oh.
So if you click the ruler symbol in the bottom, it will
I
disappear
see,
again.
yes, thank you. One day I'll learn how to use the system. Right, where were we? Back on the red pen. That was point 2.5, 2.5. And another one would be 2.5, 1.5. Another would be 1.5, 1.5. And another would be 2.5, 1.5. And the contour is going to be a rectilinear contour. It's going to be a straight line there. It's going to be a straight line there. It's going to be a straight line there. And it's going to be a straight line there. Okay, now that differs from the Euclidean distance, because if I was drawing the Euclidean distance, it would be a circle going through the vertical and horizontal points. And let's go to black pen. If I can try and draw a circle without corrupting anything, that would be the Euclidean contour. Now, what this means is at some points, The city block and the Euclidean are exactly the same. The top and the vertical top and bottom and the left and right. But in the middle, for example, this point here, that point is a distance 1 using Euclidean distance, but it is less than a distance 1 with the, sorry, say that again. This point here is a distance 1 using city block, but it is less than 1 Euclidean. So there is a distortion in the distance. Is this important? Well, to do that, we've got to look at the decision surface. And I recommend in your own time, you draw this yourself accurately on graph paper to see exactly what's going on. What I'm trying to show you here is point A and point B in pattern space, two-dimensional vectors. A equals A1, A2, B equals B1, B2. Now, to plot the contour of equidistance, let's change color. I've labeled the distances 1, 2, 3, 1, 2, 3 using city block. That point there is the intersection of 3A and 3B, and that point there is the intersection of 3A and 3B at the other side. Now, if I take the two contours, there is going to be a situation, because the surfaces are rectilinear, where you don't get a point intersection. You get a line intersection. And where I've drawn this, if I've drawn it accurately, what I'm trying to show is the line of contour 2 overlaps for A, overlaps the line of contour 2 for B. And so the point of equidistance 2 from A and B is going to be this line in here. And then if I take more contours, we would have 4 up there, 5 up there, and 4 down here and 5 down there. Joining them all up, the decision surface becomes piecewise linear. So that is the effect on the decision surface. Now, if I draw the contour of equidistance based on Euclidean, I'll try and do this without corrupting anything. The equidistance contour, don't touch me. Oops. The equidistance contour is going to be a line that comes in here. It goes out there. It is going to be a line like that, which will be the line going through the midpoint at right angles to the line joining the midpoint. And what we're going to get is an area up here, an area in the middle here, an area in there, and an area down here, where we are going to get errors. In other words, if I take a pattern in here, that point there, if I were using the Euclidean distance, it would be this blue line going through here. Let's extend that down there, which is a straight line. It would be on the A side of the blue line, and that would be classifying this pattern as closest to A. But if I'm using the city block distance, it is the green line, which goes down there, across there, and across there, and it would be on the B side of the decision surface. So depending on the distance metric you're using, this point could be classified as A of the Euclidean or B for the city block. So there's going to be a distortion. This gives rise to what's sometimes called as a dogleg decision surface. Let me draw it out separately without the contours. Oh, help. Here's my axes. There is my pattern A. There is my pattern B. The Euclidean surface will be like that. And the city block surface will be like that. I'll change color. It goes up there. It goes across there, and it goes out there. So it forms a dog leg across the true distance. Now that could be a problem, but not a serious problem, because if I have a cluster which is a cluster of points for A and a distinct cluster for B, we will get perfect separation whether I'm using the black line or the red line. But there is certain circumstances when very strange things happen. Now, going back, going back to the contours we had with the two patterns, just supposing I move B down, move B, the red contours, in that direction. We get to a point where not only does the line between the A and B's overlap, but we get to a point, if this contour is here, we will get an overlap of the distance 3 and the distance 4 and the distance 5. What this means is we will get a situation, and again you can verify this by drawing the contours yourself, but I will go straight to the result. We could have a situation where I have pattern A there and pattern B there, and the decision surface, the linear part between A and B is the same, but we get a situation where the outer contours overlap, and we will get a region like that, and a region like that, a region there, and a region there, where the contours are overlapping, and any pattern in this region or this region is going to be equidistant from A and B. So if you're using this method, we would have, say, a cluster like that of points. These patterns here would not be classifiable because they, according to the city block, would be equidistant from A and B. And that will happen on a unique orientation in pattern space. In 2 dimensions, it will happen when the line drawing A and B is at right angles, no, not right angles, at 45 degrees to any axis. So there is a situation where instability can occur, and you will find that the classifier is giving lots of rejections. That would happen if this void had opened up. And in 2 dimensions, what should be a line becomes an area. In 3 dimensions, the linear part will be a plane. This will become a volume. And in multidimensional space, we're dealing with hyperplanes and hypervolumes. Now, the final problem with this approximate distance classifier is if I move this pattern down further. What will happen then is the decision surface will follow this line, and this line. So we'll get a decision surface that looks like that. So we have 3 situations which can occur, which cause instability, particular orientations in the pattern space. This could be one situation. The second situation could be a decision surface that looks like this, where the void opens out. And the third situation is where we're following the other extreme of the void, where the decision surface looks like that. So in one case, taking the void, come back. if this is the void area, in one case we are following this part of the line, which gives me this surface. In the other case, we are following this part of the line, which will give me that decision surface. And of course, the patterns in this area are affected and give inconsistent classifications. Now, that's just for two cases. If you extend the method to more dimensions, then these are going to be hypervolumes, and the linear part will be one dimension less. It becomes a very complicated decision surface. And if we're using multiple reference patterns, each pattern will give a local behavior of the decision surface, that, as shown on those two diagrams. It becomes unreliable, unpredictable, and doesn't give the accuracy that one would hope. Now, that is the city block. What about the other decision, the other approximate distance? And the other approximate distance was the square. The square distance. Now, the square distance has got nothing to do with the mathematical squaring operation. The square distance is defined as ds equals the summation I equals 1 to d of the max operator, mod ai minus bi. And this is going to be I equals 1 to d. In other words, we take two vectors, we find the mod of the corresponding elements, and take the square distance as being the biggest difference between single elements. Right, the contour. And I'll go through this quickly because it's much the same geometry as the city block, although the method of calculation is completely different. The square contour for a pattern 2-2 is square. It is effectively the city block rotated by 45 degrees. And so that would be distance 1, that would be distance 2, and that would be distance 3. And if we then follow that through, we will get exactly the same behavior and the same instabilities with the square distance, but they will be in a different place in pattern space. So if you're using a distance classifier, you're finding you're getting a lot of rejects, patterns that appear to be equidistant. Obviously, you would be operating in that region of space where there is an instability for the city block. Change to the square distance. It might just work. Now, in using a distance classifier, most people, and to use them, most people just simply think you take reference patterns, you take an unknown, you find the closest known pattern to that unknown pattern, and that is the classification of the unknown pattern. It's as simple as that. You don't have to ever calculate the decision surface, and you use it as a very simple algorithm. 99% of users of distance classifiers simply do that calculation. But I hope now you understand the mechanism of the classification and the behavior of the decision surface and how this can lead to errors, inconsistencies, and unreliability. So there we are. That is a brief tour of a distance classifier. It's been used for many years for classification. If it works, it's fine, but it does have inconsistencies and unreliabilities. So, one final thing, if you look up distance classifiers, you will often see the kth nearest neighbor. Now, this is a way of protecting against error reference patterns. If I were to take a two-dimensional pattern space where I have a series of patterns which are class A and patterns of class B over here. Now, if I were to have a rogue or error training pattern, and just supposing a pattern from class B occurs over there. Now, if you are using the single nearest neighbor, an unknown pattern you want to classify, would minimum distance appear to be there, dmin, and it would give a wrong classification. But the kth nearest neighbor is a simple improvement on that. It says don't go for the nearest, go for the k nearest neighbors. And if I was saying k was 5, I would measure the distance of the unknown to this reference pattern. It's appeared to be the red class, but it's wrong. So we would have one distance nearest to the red. If I take the second nearest distance, it would be black or A. The third would be A, the fourth would be A, and the fifth would be A. So there's a whole region of patterns in this area, which would be classified as the red class if we were using a single nearest neighbor, but it would not be classified in patterns in this region, which are closer in the main to the majority of the A, would be classified as the A class if we're using K. And K can be a number you choose yourself. Usually 5 is a typical value. So that's the kth nearest neighbor, a simple refinement on the nearest neighbor. And the kth nearest neighbor can apply to both the Euclidean distance and the city block and the square distance. Okay, that's the end of distance classifiers. Now, just two other little problems before I leave it. The distance classifier isn't sensitive to size. Supposing I had an A class here and a B class here. The decision surface would be a line through there. Supposing I take this pattern here, which let's say it's 2, 2. And suppose that was zoomed out and it became 4, 4. So 2A equals 2, 2. Size increase. A becomes 4, 4. That would be a black reference pattern, which would be 4, and let's put it there. And again, if that was a pattern there, if that was applied as a test pattern, we know it's a class A, but there are situations where it'd be closer because of size change to the opposite class. And this is just for a 2-class pattern. If I have 3 categories, 4, 40, 400 in our pattern space, that could become a big problem. And the second other problem is position invariance. And I've got an example here, which is binary patterns. And remember, with binary patterns, the Euclidean distance becomes the Hamming distance. And we've seen that that can be calculated using the XOR operation. If I took a pattern, and let's have 3 by 3 pixel image, and I was displaying a vertical bar on that, that's my reference. And I had 2 test patterns. And the 2 test patterns are a vertical bar, which is moved slightly, and That's test pattern 1, and nothing. An empty or a white screen. And that's pattern 2. Now, the human, if I say, here's 2 test patterns, which is the vertical bar? I think everybody, including mechanical engineers, boom, boom, would say that that is a vertical bar and that is not. The bottom one, 2 is not. What's the Hamming distance? What is the distance between the reference pattern and this one? We're using the XOR operation. It really is counting, simply counting the number of pixels as a difference. It would be same, different, 2 different, same, 3 different, 4 different, same, 5 different, 6 distance. So the distance there would be 6. If I now take the blank screen, same, different, same, same, different, same, same, different, same. The Hamming distance there would be 3. The blank screen, according to the distance classifier, is more similar to a vertical bar than the shifted pattern. And of course, this leads to the need for pre-processing, because as humans, if we were looking for a vertical bar, we would center position-wise on the vertical bar. If I were to shift all the patterns to the left-hand side of the screen, a run code would do that. I would have a pattern there, which would be a reference pattern normalized, position normalized, and the test patterns would be normalized, shifting to the left. That would be my test pattern shifted, and the blank, of course, remains blank. And of course, if you do the distance classifier there, you would see a distance of 3 between those two, and 0 and 6 between there. 3 is a shorter distance, it's a vertical bar. Now, humans do that by moving eyes, moving heads, focusing on the area that you are interested in, the center of the retina. We can use image processing methods to do that for pictures, and we will deal with that, hopefully, image processing. So that really does conclude the end of the distance classifier. Right, now, neural networks. And I want to start really from basics, the inspiration behind them and how very simple models work. Why use them? And I think the first inspiration is the brain. It could be the human brain, which is really the superb processor of information. It could even be brains, because they are quite capable of doing interesting image and data processing. The second reason is learning systems. The brain learns without a program, no programming. And the third reason for looking for neural networks as a solution is they can solve problems, or we hope they can, because humans can do it, that cannot be analyzed. When the mathematicians can't produce a formula, the neural network hopefully can by a learning process. Now, in trying to find out how the brain works, top down versus bottom up. And the question is, which approach? Now, neuroscientists are firmly set in the top-down approach. They will take a brain, put it in their scanners, They will apply external stimulus to you, maybe music that you like, maybe making you hot, making you cold, showing you pictures of nice things, your partner or your mother, or nice scenery, sunsets and all that. And in the scanner, they can determine what part of the brain is being stimulated. And so far, they've discovered about 60 regions of the brain that are function specific. Very interesting. But we are dealing with a device, a human brain, which contains approximately 10 to the 11 cells. And those 10 to the 11 cells, that's a big number. That is 100 billion. Let's write it down as a number. I think that's 10 to the 11, 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That is the number of cells in a normal brain. Yes, I know some brains might have less than that, but we're not talking about mechanical engineers now. So, yeah, just looking at the correspondence. Can I go through how we worked out Hamming distance? Right. I'll talk to, email me and I'll send you information about the Hamming distance. I don't want to take up too much time going back on that. It was covered in an earlier lecture. Right. Now, the neuroscientists have their 60 regions, which are function specific. Does that give us any inclination as to how the brain works? And my answer would be no. It's like you as an engineer taking the latest iPhone 11, isn't it, that's just come out, and putting your hand or a heat detecting device on top of the phone, and then using the phone to send a telephone message, to send a Google website, to send text message, to send WhatsApp and whatever, and saying, oh, when I send a text message, this region gets hot. That's the text message section of the phone. When I send a email, another region gets hot. That's the email section of the phone. It will not tell us anything about the actual mechanisms that are inside. So I am firmly in the bottom-up approach. And what we try to do is look at single brain cells. We want to make a model of them, either mathematical or an engineering model, build them and see how they work. And the key thing is, can we identify any emergent properties from these systems? Now, this is an approach that has been going on for an awful long time. One of the models of neuron which is still used is named after two Americans called McCulloch and Pitts, and that is still used today. So how do we go about getting a model for a single cell? And the single cell is called a neuron. Now, I think at this stage, I'd like to say the aim of neural networks is not to copy and exactly replicate human brains or animal brains. A human brain is quite cheap. You can hire one for about £10 an hour. Whether it will do the things you want to do at the right time is another matter, but it certainly has the processing power, and there's 8 billion of them in the world. But what we do want is new strategies for computing. And the appeal of having a system that is not programmable is a very strong one. Most large computer software systems do not work. We're seeing it with test and trace. We've seen it with huge scheduling tasks that have been attempted and costing millions, hundreds of millions of pounds and failing. And also the complexity of software is ever increasing. It's getting beyond our human understanding. So that appeal for a system that learns without the programming, without the analysis, is a very strong one. So the human brain is complex. Let's look at a single cell. How am I doing for time? Yes, I've got another quarter of an hour. Let's draw a brain cell, something like that. And there is the output. So there is the output Z, let's call it Z. And that will then be connected to other cells. Now let's identify these lines as inputs. I1, I2, down to IN. So there is my input vector I. Right, the exciting thing, at least for electrical engineers, and it makes me very excited, the input signals are voltages. It's a complex voltage pattern, but it is potentials. And so the whole of the brain and the whole of information distribution in humans is electrical. So electrical engineers, electronic engineers should be very interested. And I think we're the only ones who are going to really crack what's going on. So there is my brain. The first question is, what goes on inside the cell? Now, we've got inputs, and some of the inputs we know will cause the output to fire. Some will inhibit the output to fire. And also, we know that some of the inputs are more important than others. Yet the voltage range on the inputs can be much the same. It's only about 100 millivolts. It's not high voltage, but some are much more significant than others. So our model let's draw it as a box. I'll just draw three inputs for simplicity, I1, I2, and I3. Those are my signals. And I want to differentiate between the effect of these. Some are more important than others, some are inhibitory and some are excitatory, i.e. contributing to the output or reducing the output. I can model that with a series of weights. W1, W2, W3. And this is a multiplication. So I comes in, it is in the first case multiplied by W1, and I2 by W2, and I3 by W3. So we now have a input vector I and a weight vector W. So the signals here at the early stage, they are enhanced, and a positive and negative signal can be put in to cause stimulation or inhibition. So we've got within the cell I1, W1. How can we combine them all? What's the simple way of combining all these weighted inputs? Well, the simplest way of doing it is add them together using a summer. And then, having got the summation, we want to determine whether the cell is firing or not. We introduce a threshold. Right, and this is basically the McCulloch-Pitts neuron model. And it's been around an awful long time. The first paper published on this was 1950. Gosh, I can just about remember 1950. Shows how old I am. So let's now have a look mathematically at what this cell is doing. Inputs weighted. So we have WI times I. Weight 1, I1. Weight 2, I2. And we are summing them together. I equals 1 to D over all dimensions. So at this point here, let's call it point X, we have is the summation of Wi, II, the summing of the weighted inputs. Now that is a vector operation. And I hope some of you from your mathematics will recognize this as a scalar. Oops. Two vectors. It's sometimes called the inner product. It's the same. Right. So what the neuron model is calculating is the scalar product of W dot I. Again, some books call it the dot product. And that equals the summation I equals 1 to D over Wi, II, the weighting of the independent elements. Right, now in 2 dimensions, we have an alternative representation of the scalar product, and it's useful because we can draw it in 2 dimensions and see what is happening. So in 2 dimensions, W dot I, the summation of product pairs, equals the mod of W, the mod of I, cos theta. And I hope you are familiar with that from your mathematics knowledge. Now we can draw this in 2-dimensional space. Again, let's have 4 dimensions because we can have positive, negative weights. This is dimension 1. This is dimension 2. And let's take an input pattern I. It is going to be I1. It is going to be I2. The modulus is the length of the line from the origin to the vector point. So that will be mod I. Let me now take a weight vector, and weights can be positive or negative. So let's go back into this point here. Let's have that point there, which is W. That will be W1. That will be W2. W2 is negative. The vector is the line from the origin to that point. That will be mod X. And cos theta is the angle between them. So that's how the scalar product looks in 2 dimensions. How can we use this for pattern recognition? Let's go to a 2-class problem. Again, dimension 1 and dimension 2. Let's have class A. There are all the points. Each one will be a vector from the origin. If I have a class B, set of other points, we know a decision surface exists which will separate them. And for this, because we're using this model, the decision surface and the vectors emanate from the origin. The decision surface will have to go through the origin. So a decision surface which would be like that, and it's not unique. It can move around as long as it doesn't impinge upon the black class and the red class. That will solve and separate these two classes of patterns as vectors. That can be defined by a weight vector, which is in this quadrant. There is W. And the key thing is for the decision surface, the weight vector is at right angles to it. And that can be achieved by setting a threshold in the original model. Going back here, it can be achieved by setting a threshold to 0, which means if we get a positive response, the cell fires. If we get a negative response, it doesn't. So one class can be determined on the diagram here. If the angle is less than 90 degrees, we will get a positive response, and this would be the positive class. I've lost it. Where's it gone? Come back. Oh, you confounded thing. System's gone down. Curses, we need intelligent systems, don't we? I seem to have lost the previous slide. Let me carry on from here. So, 2 dimensions. There was my cluster for the black ones. I'm running out of time. I'll just finish off here. And the red ones, there is the decision surface, which will separate the black from the red. It can be defined by a weight vector that is at right angles to it. So there would be my W. This would be the positive response class because theta is less than 90 degrees and we are in the scalar product using mod W mod I cos theta. And it could also be in this region here. However, if we're in this region, cos theta is greater than 90 and less than 270, this becomes the negative response class. And so we have 2 responses from the neuron. It fires or it doesn't. It fires for one class, it doesn't for the other. So that is the idea as to how a neuron can be used as a pattern recognizer. The big question is, how do we find W? And that will have to wait till next week. Okay, that's a start. Sorry I've overrun by 1 minute. Sorry about the tech problems, but if you have any problems, email me and I'll try to get back to you.
Thank you very much, sir.
Sorry about that. I'm fighting with the system, but we will win. Okay, guys, bye for now.
Thank you.
Thanks.
Bye.
Bye.